All right. Good morning, everybody. So first, let's see. I want to hear from the chat if you hear me well. So hopefully this is going to be better than last week. I've tweaked a little bit some settings and so on. So hopefully the stream is going to be more healthy. All right. So let me start first with talking about what's going on this week. So this week, what's due? It's Project Zero. Okay. So remember, Project Zero, it's going to be individual and there's going to be no late days. Okay. So it's due Sunday, 10 p.m. So the idea of Project Zero is for you to get familiar with the whole setup. Okay. And especially Docker. So by now, I'm going to assume that you all have Docker installed on your laptop and it works. Okay. So if it doesn't, please do so today. Okay. Don't wait for the last minute. Docker, especially if you use Windows, it's not that simple to install. Okay. But I'm going to assume it works and so on. So then comes the project. The project, there are two parts. One is to get familiar with GDB. And the other one is actually to contribute to the code and build something. So here, I understand this is not easy, right? Maybe you haven't actually, you don't have a lot of experience with GDB and so on, but don't focus too much on the tool. What's important is like you understand actually the bootstrapping process and so on. You understand what's going on, and you are able actually to know what you want to see from GDB. Okay, because once you know exactly what you want to see from GDB, it's easy to go online and to look and to search actually for that option. Okay. Let me be more precise here. For example, what I can tell you is that when you start the first exercise, which is actually knowing what's the first instruction that is executed by the OS, by the bootstrap actually. Well, here GDB shows you some random stuff. It doesn't make sense, right? If you look really carefully at the addresses, if you look at the instruction, and then if you try to execute step by step, then you realize something is off. Okay, something doesn't behave as it should be. Okay, again, we're doing x86 here, but it's not really different than what you have seen in B58. Okay, so here it means that GDB is not well configured. Why? For the why, actually, you don't need to look into GDB. You need to look in the handout. Read the handout, understand what's going on. Okay, if you still have issues, actually, the TAs are going to cover that this week. Okay, so they're going to cover a little bit of give you some clue about why this first at first GDB doesn't work, and also they're going to cover extensively Docker, right? Because you need to be familiar with Docker, you need to be kind of comfortable actually tweaking the Docker command and so on. Okay, so do that. All of this is going to take time. Okay, although once you know how to do all this stuff, it's kind of trivial, but it takes time. It takes some reading and so on. So don't start the last minute. Okay. All right. So we talked about the project. We talked about the tutorial this week with the TA. Just to let you know, I don't know exactly what's going to be the format of the tutorials for the rest of the semester. Okay. Most of the time, I will try to give something to the TA to show you, some kind of a demo or some kind of cover a little bit of materials and so on. But then most of the tutorial is going to be like more like questions and answers in a collective way, right? Now, if you have more specific questions or actually personal questions, we have to do it in office hours. Okay, so the TAs have office hours. I'm going to have also office hours tomorrow, Thursday. Thursday, maybe what I'm going to do. So it's going to be on BB Collaborate. At first, I'm going to open for a general question, like a public kind of forum. I will do that for half an hour. I will see if I have many questions and so on. And then after that, I'm going to move to personal questions. Okay, so if something is wrong with your enrollment or your setup at home or your Git GitHub thing and so on, you can ask me privately. Okay. So that's it for the logistic. So right now, okay, for the lectures, I'm still going to continue on YouTube Live. We will see if the quality is better this week. And I think it's great because then after that it's posted there. You can watch it after the live session and so on. So I would like to keep this set. All right, so let's start with the topic of this week. Do you have any kind of general question first? All right, no question. So let me move to the slides. All right, so last time I gave you kind of a overall picture about what an OS is about. And one of the main tasks that an OS is going to do is actually manage all the process. The idea is like on a computer, multiple processes are going to run concurrently. Right? And we saw that concurrently means actually executing one after the other, assuming we have one CPU. But from the user perspective, it looks like everything is going in parallel. Right? So of course, managing all this process and so on, it's going to be complicated. Okay, so that's going to be our first lecture, looking at how actually we manage those processes and how we schedule those processes. All right, so. First, let me make a distinction. Last time, I didn't talk about process. I talked about programs, right? But here, I'm going to try to make a distinction, actually, at least semantically. We're going to call a program, when you compile, for example, some code, you obtain a program. So it's kind of some kind of static data, and it's on the storage, right? So it could be a .exe file on Windows or an executable actually on Linux. So a process, it's actually an instance of this program. So when we decide to run a program, actually this program is going to run inside a process. What's the difference here? Well, you can have actually several processes of the same program running concurrently at the same time on your machine, right? So for example, you can open two instances of your browser. Okay, or you can open two instances. I mean, you can execute two instances of the same kind of program that you have just compiled. Okay, so that's why we're going to use this term process here. So here, this is kind of a brief reminder of the kind of architecture that we had last time. So again, that's a very simplified view, but here what we have is the memory. And the memory is divided into mainly three parts. So there is the boot part that you are actually studying this week for the Project Zero. There is all the input outputs, okay, where we're going to actually read and write on these input outputs. And then there's going to be the RAM. What's going to be in the RAM? Well, of course, we're going to have the OS, meaning the kernel, okay, with all the system calls and so on. And we're going to have all of our concurrent program inside the RAM. Each program, when they run, they need their data, okay, meaning the stack and the heap, and of course the instruction itself. At any point in time, the processor is executing one program, okay, meaning the processor has the instruction pointer to somewhere in the program, and the stack pointer to actually push and pop data, okay. While the processor is executing the program, is also listening for interrupts. Okay, interrupt means we're going to see that in more detail, but basically some I/O needs some attention. Okay, there is something ready, something that needs to be processed, and it's going to interrupt the CPU so that it actually handles this interrupt. Okay, we're going to look into that into more detail. So we saw that last time, the idea of running processes concurrently. So it's not actually running one process after the other, but it's more like we're going to run multiple processes kind of looking at the same time by giving a little amount of time to each, right? So we saw that last time. The idea is like, if you have a process A and a process B, you're going to execute a little bit of process A, then move to process B, then move again to process A, then process B, and so on and so forth until they are done. Okay. Every time the CPU executes a program, the program has the CPU, and the CPU keep executing that program. Okay. So this is called limited direct execution. We're going to execute this program until what? Well, two things, right? Either actually we have some kind of a system clock that's going to stop, interrupt and say, okay, now, you have executed this program for a while, let's stop and let's move to another one. Okay, that's going to be the system clock and interrupt. And it's there by design, right? So it's to avoid actually having starvation, meaning having one program running forever and the other one not getting any CPU time. Okay, so we have this idea of there's going to be a clock, okay, I'm going to execute you until time's out. Or as soon as actually the program does an input-output. Because as soon as the program needs some kind of input or output, it's going to take time, okay? Significant time compared to the CPU time, right? So here, the CPU is not going to go idle. It's not going to wait for the resource to be available. Instead, is going to kind of what we call preempt. It's going to stop and then execute the next program until this one is ready. Okay, so that was kind of the naive approach, and this is actually the real approach, but we're going to give more detail into that. Okay, again, so the advantage of concurrency is like from the system perspective, it's a better CPU usage. We saw it last time, if the CPU is not waiting for I/O, you execute a lot of program in less time, okay? You execute faster a bunch of programs, but not individually, right? Because individually, sometimes a program might wait for another program to kind of execute before taking the CPU, right? But from the user perspective, this is great. It looks like everything is going at the same time, in parallel, right? It's kind of like, again, we have only one CPU core here. I mean, we assume, right? So things are not really going in parallel, but because it's going so fast, like switching between process, for us, it looks like things are going in parallel. And that's why when you use your computer, you can watch a video at the same time. You can actually, type code, execute, and so on. But doing all of that, it's going to require, of course, some mechanisms to manage and schedule those concurrent processes. And that's what we're going to look into today. All right. So today's lecture, I'm going to try to answer 4 big questions. Okay. The first one is we're going to look into this business of interrupt. How does it work exactly? Because what I told you is like, once the processor has is executing your program, nothing in this program is going to tell the CPU to stop. Right? So at some point, this CPU needs to be interrupted, and we're going to see how this is handled. We are also going to talk about this idea of like switching context. We call that context switching, but the idea is like you have a running process, you're going to stop this running process, you're going to save some kind of a state, and then you're going to execute another one. Right? When you need to resume that process, again, you're going to take this process, switch the context again, and then resume the execution. Right? We are also going to look at the process API, meaning from the user perspective, how do you create process, create, terminate, process, and so on. Actually, this part you have already seen it in BO9, so it's going to be mainly recap, but telling you a little bit how it works behind the scenes. And then finally, the big part is like, how do you schedule processes? Okay, assuming that you have many processes that are ready to be executed, okay, they are not waiting for any I/O and so on. Which one do you choose? Okay, and here the idea is like we need to give fair kind of access to the CPU to each program. Right? So that's going to be the last part about scheduling. Okay, so I'm ready to go in the first part, but let's see. I'm going to look at the chat quickly to see if we have questions. Okay, so it looks like there's a lag. So I had many questions about actually Project Zero. For this question, let's move it to either tutorial or office hours. Let's concentrate on the lecture for now. So there is a question about the lecture here. How does memory get handled on the CPU cache when you are constantly switching process? Okay, assuming they don't all fit and so on. That's correct. So here actually we're going to see that a little bit, that what's happening in memory when you switch context. But of course, having all the processes in memory is not actually scalable. Right? And we're going to see that later. So there's going to be a part in this course coming week 4 about memory management. And we're going to see all kinds of techniques like virtual memory, swapping, and so on and so forth. Right now, we are only going to look at the how to manage those processes and assuming that everything fit actually in memory. Okay. All right. So let's continue. So here I'm going to look at this kind of interrupts, right? So again, the CPU is going to be interrupted when an I/O device is actually ready, or actually when there's this kind of system clock saying, hey, the time allocated to this thread as timeout. Okay, so it's going to receive this interrupt. This interrupt actually hardware interrupt. Okay, and so we're going to look at those ones. Those ones are told to be asynchronous. I'm going to try to explain this concept later on. Okay, but there is another kind of interrupt that we call software interrupts. Okay, and we call it sometimes exceptions. So this has nothing to do with the hardware, but it's more about like when you execute a program, there are two types of things that can come up. One is a fault, okay, a problem, an error. So for example, divide by 0, that's an error. Okay, as soon as the CPU does a divide by 0, it cannot actually move further with the program. It has to do something. Most of the time, stop the program. It could be also a page fault. Again, that's something we're going to look at when we talk about memory management. So I'm going to skip that for now. Okay, but again, a page fault, when it occurs, most of the time, the OS is going to stop the process. Okay, or there's also the concept of trap. Okay, what's a trap? We're going to see that, but it's basically, you can think about it as a low-level assembly for throwing an exception. Okay, you're going to throw an exception using that instruction. And as soon as you do that, it's actually going to stop the CPU and the CPU is going to do something. Why is it useful? Well, one of the main use is actually to call something we call a system call trap. Every time you want to do a system call, you're not going to call directly the code, you're actually going to do a software interrupt saying, hey, I want to do a system call. Okay, we're going to see a little bit later into detail. Okay. So here the instruction is called int, okay, and you have to pass an integer to say basically that's the number, right? So each exception can have a number, right? So here you see the difference between these two interrupts is like when you execute a program, if you have software interrupts, they are about the current running process, right? Either because the current running process is dividing by 0 or is doing something that is not supposed to, or because it executes this trap instruction, okay? So that's why here it's kind of synchronous, right? Because we are going to handle this interrupt, for the current running program, okay? And as soon as it occurs. For the hardware, it's different, right? If you follow what I said about the way I/O is done, when a process requests an I/O, so assuming the process is running, it requests an I/O, the processor is going to stop the process and then switch to another one, okay, until the I/O is ready. When the I/O is ready, what does it do? It actually sends an interrupt to the CPU. But here, when the CPU receives the interrupt, it says that some I/O is ready, but is it for the current program? No, it's actually for one of the program that was stopped, right? So we're going to see how this is actually managed. But here there is this idea of like actually the CPU is going to stop, and then update the program in memory to say, okay, your IO is ready, here is the IO, and then maybe actually resume the running process. Right? So let's go. Let's look into more detail there. So how does it work exactly, this hardware interrupt? Okay, so here we're talking really about something that is wired on the motherboard. Okay, so what's the naive implementation first? The CPU is going to receive interrupt from different devices. Okay, you can think about it as the system clock as being one of these I/O device. The keyboard, for example, as soon as there is a keystroke, it's going to send an interrupt. But the USB, the network, the ACPI, I mean, there's all kind of interrupt there. So they're all connected to something we call interrupt request lines, IRQ. Here, if it was really like this, meaning, the CPU has a certain number of IRQs and, each device is connected there, it wouldn't be very flexible. Why? Because it would be, first of all, hardwired. And also here, the CPU might be interrupted all the time, right? So what if several interrupts come at the same time? Can we do something more kind of flexible, right? Also, how to handle priority, right? So you have several interrupts at the same time. Which one has more priority, right? For example, as a keyboard keystrokes has more priority, for example, than, I don't know, the network or even the clock, right? Maybe not. So the real approach, what's actually implemented on your computer, is this. So here, the CPU actually is not connected directly to all these IRQ lines. Instead, it has one big vector. So here I'm looking at this part here. It has one big vector called an interrupt vector. Okay, and it's like some kind of an input-output, which is, somebody is going to write some kind of a number there. And as soon as there is this number, the CPU is going to say, oh, wait, I have an interrupt. It's going to read that number. And based on that number, it's going to do something. Okay, we're going to see that later. So here it's actually a big vector. It's 256 bits. So here, the number of interrupt that you can have is actually huge, right? From this vector actually is going to receive all of them. The hardware interrupt and actually the software interrupt that I didn't talk about in the previous slide, which is even a divide by zero, a page fault or a trap. All of that are going to come to this interrupt. So from the CPU perspective, it doesn't matter really if it's hardware or software. What matters is as soon as we receive an interrupt, it reads a number. Based on that number, it's going to do something. But how are the hardware interrupt managed? Well, they are managed by something we call a programmable interrupt controller. So that's actually a chipset, and there are two of them, a PCI master and a PCI slave. And here they're going to manage the interrupts. So here, as you can see, for example, the keyboard and the clock, which are actually quite important, they are connected to the PCI master. Okay, meaning they have a RQ line, and you know that, for example, when it comes to RQ0, you know it's the clock, and that's actually pretty standard on computers. Then the PCI slave it's also connected to this PCI master, and here it has other kind of interrupts. Okay, so for example, there's another clock called the real-time clock. Okay, the clock of your system. Okay, not the one that, as opposed to the system clock. The system clock is the one for the thread, the scheduling, right? But also all the stuff like the USB, the PCI, the network, and so on and so forth. So all the kind of secondary hardware that are not as important as the keyboard, for example, they're going to be on those interrupts. So why do we have that? Why do we have these two chipset and so on? And what does this chipset do exactly? Well, they are responsible to tell, for example, the CPU when there is an interrupt. So basically write on the inter vector. But the good thing with that is you can do a few things. First of all, they're going to manage priorities. If many interrupt lines say that there is something, well, it's going to do something. And it's going to give priority to the lowest actually RQ lines. So for example, RQ0, that's why it's the clock. This one has the highest priority. Okay, the second one actually being the keyboard. And also they can be masked. Why is that useful? Because as we're going to see later, as soon as you have an interrupt, it means the processor needs to do something. And to avoid actually being interrupted another time, what it can do is actually it can mask some interrupts. Okay, not all of them, but some of them. So for example, if it receives a keyboard stroke, it can actually prioritize that over the network, for example. Okay, but it can be masked, but also it can be not all of them have to be masked. So for example, if you are doing some kind of interrupt on the keyboard, still the clock can actually have priority and is not masked and is going to interrupt the interrupt handler. Okay, so you can have interrupt of interrupts here. So that's actually what the PICs are doing. Okay. So how does it work when you handle an interrupt? So what the CPU receives is a number on this integer vector, and then for every entry of, there is a big table, okay, called descriptor table, interrupt descriptor table, and then for each entry there is going to be a handler. Okay, this is not hardwired, not hard encoded. You can actually tweak and decide what all these handlers are doing. Okay, so here, for example, there's going to be one for the time interact, one for divide by 0, one for the system call, one for the when there is a keystroke, and so on and so forth. Okay, when the handler is executed, I told you, right, this is an interrupt, meaning the CPU is going to stop whatever it's doing. Okay, it's usually going to save something about the program, so it can resume later. Then it's going to execute the functionality, okay, and then restores the current program. Okay. So where does interrupt define? Well, on Linux you can actually look at /proc/interrupt. On Windows it's going to be on msinfo32.exe. And on Pintos you will see that it's actually inside interrupt.c. Okay, and actually if you look at this file, you're going to see the two PCIs, the slave, the master, and so on. So it's going to be like, everything I just talked about, it's going to be there in the code. So let's give a quick example here. Imagine you press something on the keyboard, right? What's happening exactly? As soon as you press a key on the keyboard has a controller, and this controller tells one of the PICs that there is something that needs the attention of the CPU. Okay, so it does an interrupt on RQ lines 1. The PIC, based on its logic, it decides whether the CPU should be notified, and if the CPU should be notified, then it translates the RQ1 into a vector number. Okay, and this vector number corresponds to an entry in the table. So what does the CPU does? As soon as it receives this interrupt, stop the current running program and then invoke a handler, and that's going to be the handler for the keystroke, for example. Okay. Most of the time, what the handler is going to do is actually going to read at the keyboard. So now it's going to talk to the controller and say, okay, can you give me the key that was pressed? And then it's going to do something. What's this handler is going to do? Probably it doesn't know which program has required that, but what it's going to do is actually going to write that into a file. That's typical of Linux. Everything is a file there. So it's going to write that key into a file and then resume. Then the OS is going to take over later to say, okay, there is a keystroke. Okay, what's the active application? What's the one that has the focus on the UI? And then provide this stroke. But usually the handler doesn't do that. Okay, so the handler, after writing this in a file, actually restore the current running program. Okay, so that's why this is happening really fast. So every time you actually press the keyboard, there is an interruption, right? You are basically slowing down the processor a little bit to actually record all those keystrokes. Be on the scene, whether the OS and the programs use them or not, right? But every time you type on the keyboard, it's happening. So that's a little bit in the interrupt, right? So what's important here, as you can see, is like there is this concept of, the CPU has a lot of interrupts, okay, 256 bits. For each interrupt, you can define a handler. As soon as there is this interrupt, this handler is going to be executed. Okay. The kind of interrupt we have, it's either I/O hardware, or it can be actually software interrupt, okay, like traps, fault, and so on and so forth. All right. So let's see. Let me turn to questions. Okay, is it PIC or PCI? No, it's PIC. It's PIC. At some point, let's see, I'm looking, no, yeah, you're right. It's actually PCI. Or is it PIC? I have a doubt. Okay, I'm gonna check that. Sorry about that. I will check my stuff later, but I will correct the problem. Most probably it's PIC. Yes, programmable interrupt controller. Yeah, PCI is something else. PCI is another controller inside. So let me, I cannot correct it here. Okay, I'll fix that. Sorry about that. Let's see, other questions. Okay, do you mind re-explaining masking the interrupts? So now that you understand a little bit this handler, let's go back to this picture here. So masking has something to do with actually priority. Okay, imagine here you have, let's say, you receive a connection on the USB. Okay, something is ready on the USB. So here, the system might have decided that actually the USB has higher priority than the network. Okay, it's as I show here. But it has a lower priority than the clock, the system clock, or the keyboard. So what's happening here? Imagine there is a keystroke, for example. When the keystroke is actually sent to the CPU is going to actually handle it. But because the keystroke has higher priority than the USB, what you can do, what the PCI master actually is going to do is the following. As long as the CPU is treating the interrupt, what's going to do is going to mask all of these ones. Okay? Meaning the only one that can actually reach is going to be RQ0 here, which is the clock, right? Because the clock has higher priority. So you can mask some interrupt temporarily. Masking doesn't mean that they're not going to be handled. They're going to be handled later, but it's just like, okay, I'm going to mask those and wait for the interrupt to be executed before actually resuming. Okay, so that's the idea of masking. Each interrupt is a unique 256 vector. No, actually, so as you can see, the hardware, usually there are, if I'm correct, I think there are 15. But in recent systems, maybe they have 24 or something like this. So 24 hardware interrupt, that's not many. After that, there is all kind of other abstraction, right? So for example, the USB controllers, you can have multiple stuff connected to the USB because you have many USB ports, although they are connected only to one interrupt. Okay, and there is a USB controller dividing that as well, right? So basically, you can extend that picture again with layers of controllers doing stuff. So that's important. So hardware, I think there are 15 or 20, so a low number. And you can have many actually software interrupts. So that's why here you have actually 256 bits that you can use, right? So a lot of numbers. So do we have like 2 to the power 256 entry on the table? I need to check, but no, I don't think so. There is actually 256 table. The idea is like you can actually tell the CPU that you have actually multiple interrupt coming. Okay, but that's configurable. The interrupt is not the interface to the device. Okay, later on the CPU and so on is going to talk to the device by other channels like the in and out. The interrupt is purely like like a ring, like a bell saying, "Hey, there's something going on. Okay, can I have your attention?" Yes, the IDT is the interrupt table. Yes. Yeah, actually, the latest question here, is it correct to say that it must store the value to a file since the program requires is now in the ready state? Yes, and that's actually what we're going to talk about now. Okay. All right, so let me continue here. So now we're going to talk about this context switching business. So now that we understand interrupt a little bit more, let's see how we switch our process. So again, assuming we have only one CPU core, we're going to assume that only one process at a time is running. Okay. So in terms of state, only one process is going to have the state running. But there can be several processes that are waiting for an I/O. Okay, and actually there can be several processes waiting for the same I/O. For example, they wait for the disk, right? And you can have several processes that they don't wait for any I/O, but they are there, they're ready, but they are not running. Okay, so you have at least three kind of state: running, waiting, and ready. If I try to kind of give you a graph, it would look like this. So first, when a process is created, it's ready. So here, it means that it doesn't have the CPU yet. It's ready to be executed. And then at some point, this process is going to be elected as the running program, and we're going to see how. Once it's elected, now it's running. It's running until what? Well, until you receive an interrupt. Either it's going to be a timeout interrupt saying, "Hey, your time to execute is over. Okay, now I need to put you back in the ready state." Okay, so there's going to be some kind of a context saved there, and we're going to put back this into ready, and then elect a new one, of course. Or actually, the process is running. It's not running out of time, but suddenly it has to do an I/O. Okay, and when it does an I/O, usually it does it via a system trap. Okay, it's not going to do directly the I/O, so it's going to be some kind of a software interrupt. Here. So it's going to be a software interrupt. But same thing, it's an interrupt. Here, as soon as you do that, the process is going to be put into waiting. Okay, meaning, okay, I'm going to wait for the I/O to say something. And of course, while you put the one on waiting, it's going to elect a new one to actually be running, right? So what else can happen? Well, now you actually, the CPU receives an I/O interrupt. Okay, meaning there is some piece of data ready, or there's a keystroke or something like this. Okay, so in that case, there's a hardware interrupt, and here that's exactly what Jackson was asking here. Well, there's a handler that actually going to look at the I/O. Is going to try to find the process that was asking for this I/O, and then change the state of that system. Okay, and of course write into a file. So it's going to put back this process as ready, and it's going to execute when it's going to be elected. Okay, so that's the idea. Something I haven't said, but basically, if there is a fault or if there is actually an exit, okay, a stop, well, the process is going to be terminated. Okay. All right. So all of that changing state of processes, we call that context switching. Okay. So again, everything I said, I'm just going to kind of repeat again, right? So when the OS receives a fault interrupt, okay, what's happening? Well, usually it's happening on the current running program. So as soon as this occurs, it's going to suspend the execution of the process and actually terminate the program. Okay, terminate the process. Maybe I should write the word process here. When the OS receives either a system clock interrupt or a system call trap, meaning the OS actually has requested a trap, it's going to suspend the execution of the running process, save its execution context, okay, change its state. Actually, here it's either to ready or to, this is actually inaccurate, ready or to waiting, okay, in the case of a system called trap. It's going to elect a new process, okay, from the ones that are ready, and then change the state to actually running. It's also going to restore its execution context and resume its execution, right? When the OS receives any I/O interrupt, okay, what it's going to do is going to do the execute I/O operation, switch the process to a ready state, the one that was waiting for the I/O operation, and then we resume the execution of the current program. Okay, so as you can see, if we want to do all of that, the OS needs to keep track of information about the process. This information is, first of all, the state. Okay, it's either running, waiting, or actually, I forgot the last one here, but ready. And it needs to keep track of the execution context. You know, when you stop a program and you want to resume it later, you need to know what's the state of the registers, all of them, including the stack pointer, the instruction pointer, and so on. You need to, of course, record the entire stack and the entire heap. Those actually are already in the memory, right? So maybe you don't have to do anything than just like, you know, leave them there. But in some cases, actually, you're gonna take them away from the memory. Okay, we will see that later. So as I told you, we need to keep track of information about the process, and this is called the process control block. It's some kind of a big struct. It's a big data structure to record process information. This is usually it's huge, right? So if you look at the Linux one, it takes, it has a lot of information. But here, what are the most important information? One, a process ID, of course, okay? Because each process will be identified by some kind of an ID. And the parent process. We're going to see that when you create process, but every process is created by a parent process. Of course, except the first process, right? What we call the root process. We need to keep track of the state. Is it running, ready, or waiting? And we need to keep track of the registers, okay, including the stack pointer and the instruction pointer, of course, because when we want to resume, we need to actually resume where it was. The user, that's going to be useful when we talk about user space in 2 weeks from now. The address space itself, okay, and so here you might say, like, why recording the address space? Well, it has something to do with what I discussed last week, which is at some point we have virtual memory, and virtual memory means we need to keep some kind of a translation table from the virtual to the real memory. All right, so that is also going to be stored somewhere. The files that are open, you know, every program is going to work with files. Actually, one of the 3 trigger one on Unix is stdr and stdout and stdin. So these are open, and we need to keep track of that. Okay, and others. I mean, there are plenty of others that are there, but at least the minimum is those ones. And then, so each process, we're going to have information about this process. And then the OS is going to maintain a queues of this process information of these PCBs. Okay, so there's going to be, of course, one queue for the ready state. Okay, so we're going to see all the processes that are ready. Okay, and that's going to be a queue. You will see that later with the scheduling. And we're going to have actually not one, but multiple queues for all of the type of the IO requests. Okay, why do we have that? Because once you receive an interrupt, it's going to say, oh, it's an interrupt, it's a keyboard interrupt, or it's going to be a disk interrupt, or, you know, USB interrupt. And so you're going to keep like multiple queues for each type of request. So, you know, for example, oh, it's a keystroke. Okay, let me look at the queue of who was asking for keystrokes, for example. Okay, and so on and so forth. Of course, there can be some management of this queue, right? You can move things around. So, for example, if there's a keystroke, you can maybe shuffle, depending on which application has the focus, about who should receive these keystrokes, and so on and so forth. Okay. But also, for example, for the disk, well, you know, if one process has received, needs some data from the disk, well, assuming the disk is going to do that first, you know, all the others are going to wait to actually place their request, right? So there's going to be multiple queue in the waiting state. So that's why. So what was important about that part? This part, as you can see, we have multiple processes running concurrently, and we need to keep track of some information about those processes to make sure that, you know, to know whether they are actually waiting or ready to be executed, and also about the execution context. And every time we actually switch the running process, we call that context switching. Okay, we actually switch the CPU execution context. Okay, we restore the registers, we restore the heap and so on, and we keep on executing the program. Okay. So let's see. I'm going to turn to questions here. Okay, can you explain again why we need multiple queues? So actually, imagine the following. Imagine program A starts executing and then needs something from the disk. Okay, so here is going to place a system call and say, hey, I need the data from the disk. Okay, fine. So it's going to be put in a wait state. At the same time, what the syscall is going to do is going to actually talk to the device and write some kind of a request on that device. And then the device is going to work on it. Okay, so this is going to take some time. What if process B here comes and say, oh, I also need to write something on the disk. Okay, but wait a second, can the disk actually manage a concurrent request? Okay, well, let's simplify it. Let's say no. And it doesn't manage concurrent request. So in that case, even that request is actually going to be waiting for, the request from process B is going to wait for request from process A to actually be being resolved, right? So that's why here we need to kind of have all these queues so that, once the disk actually send an interrupt, okay, you know that this data is ready and it's going to be for the first one in the queue for program A. And then you're going to remove program A from the queue. And now you're going to be able to process actually the request from program B, and then again wait for the request and so on. So it's very actually useful to have all these multiple queues so that you don't have one gen being queue with everything that is waiting for an IO. Okay, because imagine you're receiving some kind of a network packet. You have to go to all of these elements in the queue to see, okay, who was waiting for the network packet here. Okay, so it's better actually to have multiple queues here to manage that. Yeah, ready, it means ready to be executed. Well, okay, I use the word ready also when the hardware, for example, a disk, you're going to ask the disk to read a piece of data, right? So once the disk is actually ready, meaning he has read the data and so on, he's going to put it on a controller. It's going to tell the CPU that the data is ready, okay? But here it does that through an interrupt, right? So yeah, okay. Here I've used the word ready for two kind of concept, but you can see it here that there's a concept. Yeah, there's a difference between process ready waiting for the CPU and an interrupt that says basically that some hardware data is actually ready. Yeah, on the keyboard, every time you hit the key, there is actually an interrupt. I will tell you even there's two interrupts. One when you key down and one when you key up, when you release the key. Mouse click, same thing. It's going to be an interrupt. Okay, actually the mouse has lower priority than the keyboard. But yeah, it's going to be an interrupt. Every time you move the mouse, it's going to be like plenty of interrupt. Okay. All right, so let's talk about the process API. So what's that? Well, let's talk about actually what you did in BO9. So here there's going to be nothing new, but it's good to actually recap on that. So basically what you're going to look at, how do you create and terminate a process? Okay. You can do other stuff like communicate, get information, control the process, meaning stop and resume. I'm not going to go into the detail, but what's important here is more like create and terminate the process. So how do you create a process? Okay, So here, the idea is like in every operating system, by the way, Windows, Linux, and so on, a process is created by another process, okay? And there's always a concept of like child process and parent process. Of course, you know, there's a chicken and egg problem here. There is a process 0 that is actually created by the bootloader, okay, by the OS when it starts. And usually this process has the process ID 0, okay, and every other process has this process as an ancestor. So it's like a family tree in a way. What you have is this kind of it's a tree, okay. At the top is the root process, and then all the kind of child process and their own child and so on and so forth, right? So you have this kind of tree data structure. So how do you create a process? Well, in Linux, Unix systems, even Mac, well, you have this fork. Okay, so you have seen that in BNI. So when you call fork in the middle of a program, what does it do? Well, actually, maybe I can show you a little bit of code, just to refresh your memory. Let's see a fork example here. Okay, let me make this bigger. I'm not going to execute this program. I'm going to share it with you if you want. Okay, it's not on GitHub yet, but I will. So what is this doing? Here, very trivial. It's actually, there's a main, okay? And the main here, we're getting the process ID of the current program, okay? And I'm going to call it parent here. Then I'm going to call fork. And fork here doesn't take any argument, so that's it. But fork returns a result. Depending on this result, okay, you will know that either you are actually in the child, okay, and here the child process is going to be executed here, or the parent process. And if you are in the parent process, you know it's going to be executed here. So how do you know? Based on the return value of that. So as soon as you do fork, in a way, it's like the parent is duplicated, but then from now on, you know, the parent is going to be executing that part, that piece, and the child is going to be executed that piece. Okay. So it's kind of strange. Okay, but you know, once you see it, it looks strange, but then after that you will get used to it. So here, actually, let me execute because that's interesting. Let's go to the desktop. It's inside lecture 2. Okay, let me compile that program, the fork example .c, and the output is going to be fork example without anything. Okay, so let me execute. Okay, so you see here, what happened is the following. The fork has actually created a child process, and here you see it says I'm the parent of the child, and then gets the PID. So here you see when so here it's actually the parent. This line here, how do you know the parent PID? Because here we can use get PID. Okay, and we know the child actually PID thanks to RC, because RC is going to be not known. Okay, so RC here is going to be the PID of the child. But for the child, it's different. Why? Because the current PID actually, now you can just call get PID, right? And of course, it's going to be different than the parent one. Okay, so here, the PID is going to be the child PID. Okay, and then here, if you want to know the parent PID, you can just, you have to pass actually that variable to the program, right? And here, interestingly, the child has access to this variable here that was declared earlier. Okay, but how about RC? RC here, well, as this condition says, RC is actually equal to 0. So you see here we have two processes. They, of course, they don't do this. They don't do the same thing, although they could. They could, by the way. But the only difference is the value of course, get PID. It's going to be different. Okay, and this RC thing here, this RC variable. Okay, here it's going to be available in both, but here the value is going to be 0 for the child, and here for the parent it's going to be the child ID actually. Okay, so it's quite interesting way to create a process, right? So again, if I try to look at the slide, when you call a fork, what's happening? Well, you create and initialize a new process control block. Okay, so you're going to basically create it, and then you create a new address space, and you initialize it with this address space with a copy of the entire content of the address space of the parent. So it's kind of weird, right? We're going to duplicate everything. Okay, even actually the instruction pointers and so on, even the code. And then what? Oops, sorry. We are going to initialize the kernel resources to put to the resource by the parent. So all the open files are going to be the same as well. Okay, so you share the same variables and you share the same open files. Okay, and then you place the PCB in the ready queue state. So as soon as you fork, you place the child inside the ready queue state. So right now, the child looks exactly like the parent. But there is one tiny difference. Here there is one exception, which is, again, I can show you, the difference is this RC. So here, oops, I can close that. This RC, so here when you fork, there are two different processes. They are exact copy of each other, okay? Two separate PCB, but the same data. But here, the RC value is going to be 0 for the child and then non-zero for the parent. That's it. And then when they're executed, this is where they take different path because of this if here. Okay, but they could actually do the same thing. So that's quite interesting about how fork works. On Unix, you have also another one, which is called exec. So I don't know if you have seen this one in Bio9, but it's also very useful. What this one does, it's quite strange as well. What it's going to do, it's going to stop the current process and actually change everything. It's going to load the new program. So meaning, the text part of the memory, it's going to change it and load the new program. So meaning the old one is no longer going to be here. Into the address space. And then it reinitializes everything. It reinitializes the hardware context, the files, everything, even the stack and so on. Even the instruction pointer, okay, with the new program. And then place the PCB in the ready queue state. It's kind of strange, right? Because I told you exec is for process creation. But actually exec does not create a new process. But often we're going to use exec and fork at the same time to actually create a process. It's really interesting. So why do we have fork and exec? Fork is actually very useful because taking alone, when you fork a child, you don't have to initialize this child with data and so on. You don't have to pass data to the child. You don't have to pass files. Everything is there. Okay, so sometimes it's actually a very simple way to create a process, and it's quite convenient. Let me take an example. Imagine a web server, and probably you have done that in Bio9. A web server, it works like that. You receive a request from the network. Okay, you're gonna create another process to handle that request. Why? Because we want multiple requests to be processed at the same time. So how do you do that? Well, as soon as you have accept, on the socket, you have an accept. You create a fork, and then here you can handle actually what was in the socket. Okay, and you don't need actually to pass data and so on and so forth. You just fork, and the child process will have everything it needs to actually handle the request and then terminate. Right? So that's very convenient. But why exec? Well, let me show you an example. So if you combine fork and exec together, what you obtain is something we call spawn. Okay, and you see that sometimes, we talk about spawning a process, or we talk about sometimes actually you use libraries that have the capability to spawn a process, right? And when you spawn a process, what's happening is that it's a mix of fork and exec. you actually create a sub-process. This process has everything, can access all the variables and file descriptors and so on from the parent, but it's a completely new program, okay, which actually fork doesn't do, but exec does. So this is quite interesting. Let's look at an example here. I'm going to take the example of, imagine you want to build a shell, okay, which is very convenient. So if you want to create a shell, here's what's going to happen. So I'm not going to go into the detail here, but what's going to happen is the following. You're going to wait for keyboards. Okay, so as soon as you have some kind of a stroke on the keyboard, okay, you wait for what? The new line character. And when you have the new line character, okay, now it's time to do something. So what do you do when you have a new line character? Okay, well, you're going to fork a process. Okay, and for that you're going to pass the line, okay, to the process. But you know, if you have read the line, you don't need to do anything. As soon as you're going to fork it, no, this line variable is going to be available here. So let's look at what doExec is doing. What doExec is doing is the following. It looks at the AV here, which is the line, okay, which is stored earlier. Okay, so that's tooling. I'm not going to go into detail. You can look at it alone. But here it's going to do exec. Okay, so remember what we have done here is like as soon as we get the line, we fork. When we fork, we have a child process that is going to handle the request, a little bit like the web server. But here it's going to call exec. Why? Because this is actually going to be executing the command. And when you execute the command, you know, you are no longer gonna resume, you know, with whatever is coming here. Okay, what you're going to do instead is you're going to execute the new program. So that's why you're going to change all the variables, you're going to change your code and so on by calling exec. But you see, at the end of the day, it's the combination of fork plus exec. Okay, so maybe you're gonna wonder, why doing this as complicated? Why not just like doing fork and exec all together here? Okay, why not just having something that's called spawn that actually fork and exec right here? Well, having these two steps, first fork and exec, actually this is how Linux has been built because of the way shell terminals have been designed. So imagine the following. Inside a shell, what you can do is using, well, let me start actually with redirection. You can have redirections. What is a redirection? Well, you can actually, so a shell when it executes, by default, it prints stuff on the terminal, okay? And it gets the input from the keyboard. That's by default. But you can choose actually to execute a program and say, oh, don't take the input from the keyboard, but take it from the file. Or don't write the output to the terminal, write it on a file. So how would you do that? Well, so here you can use basically redirections. And so what you're going to do is like, you're going to look at the command. Of course, you're going to parse all this redirection to understand, okay, is there a redirection or not? And then, you know, you fork again. But now when you fork, okay, you're going to look at, you know, what is the input file? Okay, is it the same as the parent or do I need to have another one? And here, if you need another one, okay, now you can actually open it. So here you open the redirection, okay? Whether it's actually the input or output or error, right? The three of them. And then you open them. And then once you have done that, now you can exec your program. Okay, and when you're going to exec the program is going to run still right actually to the input, output, and error without actually knowing, I mean, it doesn't matter, without actually knowing whether it's a keyboard or it's actually a file. Okay, that's how the magic happened. And the magic here happens thanks to this disconnection between fork and exec here. Okay. And the fact that we're going to be able to parse and connect the files and so on inside the chart. Okay, so we're not going to do that inside the parent thread. Okay, this is the magic of how redirection works. And then if you want, you can add another extra layer, which is, let's add pipes. Okay, what are pipes? It's basically, you can stream the result of one command to the input of another command, right? So how do you do that? Well, it's exactly the same, but now there's going to be actually multiple layers. Let me show you. So here it's still the same as before. You're going to fork, but now you're going to parse, of course, the command. But then the first thing you're going to do is you're going to connect all the pipes. Okay, so you connect all the pipes, and for that you're going to switch another fork. Why? Because now you're going to connect the individual commands between those pipes. Okay, and those commands can contain redirections. Okay, so you see here you can have actually pipes and redirection together. And here, when you do that, now you're actually going to do the redirection piece here. Okay, so and all of that works magically. I mean magically, well, thanks to this kind of disconnection. And then after that, you execute each command separately, right? So you see here, I mean, if you didn't have this mechanism, if you were to create this shell with pipes and redirection, just having a spawn instruction, it will be very complicated. Okay, or at least the logic would not look like as nice as this one. Okay, so let's go back to the slides. So again, I'm going to share this code with you, and so you can look at it and execute it yourself. But again, the fork and exec are very kind of Unix style, right? There is actually some kind of argument that fork is actually dangerous. And the argument comes from Microsoft, because Microsoft has a different approach. On Microsoft Windows, they don't have a fork. They have create process, which is some kind of a spawn, right? And it's a choice, right? Because they believe actually there is a security issue with fork. And they're actually not, they are not wrong, right? They're correct. When you do a fork, as a programmer, you have to be very, very careful, okay? Because what you're going to do in the child, you have to be, so if this program, for example, deals with inputs and so on and so forth, or, deal with the users, and the user can actually manipulate the child, it can be dangerous because the child has access to all of the variables and file descriptors function as the parent. So if you use the parent-child kind of thing to outsource some computation, but at the same time you want to kind of like shadow the computation, or you want to kind of like hide the computation, well, you have to be careful with using fork because you share everything. Okay, so that's why Windows has actually a different creation process. They have something called create process on Windows, and this will actually behave as a spawn, meaning it creates and initializes the PCB, it creates and initializes a new address space, it loads the program into the address space, copy the arguments into the memory. Okay, it's going to be the same arguments, but the context is going to be, you can tweak that. Okay, you can tweak that actually inside the command. Okay, and then place the PCB on the ready queue state. That doesn't change. Okay, other stuff, just as a recap, you can wait for the process. So here, when you execute, which process is going to be executed first? Is it the parent or the child? And in BO9, we told you, well, we don't know. And it's true, right? We don't know. It's going to be, based on this scheduling thing that, it might be the parent, maybe the child, we have no clue. So sometimes we need to synchronize them a little bit. Sometimes we would like to have the parent coming, doing something before the child can do other stuff, right? So for that, you can use the command wait. Let me show you an example here. Here, for example, you can do something like this. So here, I have the parent waiting for the child to terminate. Okay, so here, I'm going to say, okay, can you wait to terminate? And I'm going to get back the return value just to check that everything was fine, right? So wait is kind of a simple instruction. You have wait on Windows, on Linux. and on Windows, it's some kind of an object. Okay, the object is called wait for single object. You can also terminate the process. Okay, so you can basically, so you can say abort. Okay, it's more than return. It's just like, I want to stop right here, and so on. So on Unix it's exit, or on Windows it's exit process. And usually when you do that, there is the OS who's going to take over to clean up stuff. It's going to clean up the threads, it's going to clean up the files, clean up the network connections, memories, and so on and so forth. And of course, remove the PCBs from the queues, right? So, yeah. All right, so that was kind of like, in a nutshell, what the Process API does, right? But you have seen all of that in BO9, it was just like some recap. Let's see. What happens if RC returns a value smaller than 0? It means there is a problem. Okay, the OS somehow had an issue creating a child. You might be running out of memory. You might be running out of process ID. That would be weird, but why not? For any reason, the return code is going to be something negative. Yeah, Tony answered. If you run out of memory, yeah, that's a good guess. How does Windows handle process? No, actually, everything I talked so far. Of course, there are some kind of details, implementation details, but everything I'm talking so far, all these kind of different process, different queues, process state, and so on, Windows is doing the exact same thing. So it's not different. Okay. Here I just talked the difference between Windows and Unix because the API looks different, but otherwise, managing scheduling process, it's exactly the same. Okay. In concept, in implementation, it is different. Can you possibly set up a redirection in the parent and then spawn a child so that the child is redirected to the file? Yeah, you could do that. But again, the idea is like, imagine you want to spawn, you are on the shell and you want to have multiple commands. Okay, you can do that. You can basically have concurrent commands. It's better to delegate all this stuff to the child, meaning all the parsing stuff and so on to delegate it to the child. But otherwise, yeah, you could do it. All right, let's see. Okay, we still have half an hour. Let's talk about scheduling. So the answer I'm going to try the question I'm going to try to answer here is, okay, you have several programs in the ready state. Which one do you choose? Okay, and other questions as well. If you have multiple programs, of course, you're going to try to give kind of a fair amount of time to each of them. But how do you do that? Do you give some priority? Are you going to execute some programs more than others? And so on and so forth. And this has to do with scheduling. So let's look into that. Scheduling here, this is an old problem. It's not only for microprocessors, right? But for anything where you have jobs, okay, or tasks, and you have workers, and you want all these tasks to be taken care by workers. Okay, so what are my tasks here? My process, and what are the workers? The CPUs, right? And here the idea is like, which job should I assign to which CPU, and for how long? Okay, should I ask, one, even if it's one person or CPU, should I ask this person, okay, can you work on task A and B, but work 1 hour on task A, 2 hours on task B, and then start and then again, right? So how do we do all of that? So this is complicated, and of course we're going to look at only with one CPU, okay? But even one CPU, how do you do all of that? Well, let's look into that. The first important thing is like, what you want to, when you schedule tasks to a worker, okay, or to when you schedule process to a CPU, you want to avoid something we call starvation, which is a process is primitive for making progress. Basically, there is one task that the worker never work on. Okay, because of the scaling algorithm, is busy doing other stuff. Okay, what if I tell you, for example, I send you 3 tasks, and I tell you, work on these 2 tasks first because they are super important. When you have time, work on the 3rd one. But what if you never have time? Because these 2 tasks take you a lot of time, right? So here, the 3rd task is going to be starving. So this is usually a side effect of the scaling algorithm, right? So either because you have priorities into your process, we're going to look at that, or it could be also a problem of resources. Okay, imagine the 3 process needs the disk, and there's always one process beating another one getting the disk. Okay, so some kind of a bully. Well, that's also a problem, right? So it can be either a problem of scheduling or a problem of synchronization, getting a lock. So when you look at scheduling, you're going to try to measure about how efficient is your scheduling. And here there are multiple criteria that you can look at. And here I'm going to give you 3. The first one is going to be the throughput. What's that? The number of processes that you complete per unit of time. Okay. So for example, here in 1 hour, how many tasks can you execute, and actually can you be done with it? Right. So so here we're going to see that. And we're going to see that the throughput can be different for the scheduling algorithm, right? What if, for example, I have one task that is half an hour and one task that is 10 hours? And if I tell you first, work on half of the task 1 first and then work on task 2. This scheduling algorithm, after 1 hour, you will not have completed any task. Okay? But if I tell you work on the small task first, after 1 hour, you will have completed one task. So the throughput here is going to be different. We'll see. There's going to be the turnaround also. The turnaround is going to be like, the difference between when the task starts the first time and when it finishes. Okay? So that's going to be the turnaround. And also there's going to be the response time. Okay? Which is actually when are you going to start with that task? Okay? So here, for example, the difference between the two is like, you can actually have a response time really fast because, as soon as they give you a task, you're going to work on it. But because you're going to stop working on this task, and you're going to procrastinate or whatever, or do other stuff, the turnaround may be very, very bad because it takes time to complete the task. Okay, so here, if you look at what's better for these 3 things, for the throughput, the higher is better. Of course, the more you can achieve in 1 hour, for example, the better. Turnaround, lower is better. Okay, of course, if you can finish a task, not long time after starting this task, that's great. And then response time is like, the lower the better. Same thing. I give you a task. If you can start working on this task as soon as possible, that'll be great. Okay. Of course, you cannot achieve the 3 of them. So it's going to be some kind of a balance. And all of this is going to be affected by what? By the CPU utilization. Okay. How much CPU you have. Okay. And also the time each process is going to wait in the ready queue. Okay, so we're going to look into that. We have also to balance this criteria. So I told you, like, what is best? Well, it depends actually. Let's consider 2 types of applications. For example, batch application, meaning all the stuff that can run in the background, or all the stuff that you can actually process it, and then you get the result when it's ready. Some kind of data processing or something like this. So this is typical of supercomputers. You give a task and then you're going to wait for the calculation to be done. Okay. For this kind of task, what you want is a good throughput. Again, what's the throughput? Here, it's the number of job per hour. Okay. Why? Because if you have a supercomputer, you're going to try to find a scheduling algorithm that maximizes the task done. Okay, per hour. Okay, because that means that you are kind of efficient with your hardware equipment. But if it's an interactive system, like for example me using my computer, okay, it's going to be different. What I want is to minimize the response time. Okay, What I don't want is like, the OS telling me, oh, wait a second, I'm busy with other stuff, I'm gonna get to your app whenever I have time. Okay, I don't want to hear that. What I want is like, I start an app, it starts right away. In practice, you don't want to minimize that too much. What you want, it's going to be a balance. Sometimes users, what they prefer is they want something predictable. It doesn't matter if it takes a bit of time to start, but I don't want it to start after 20 seconds, right? But if it takes 1 second or two, it's okay. Okay. If this is actually a trade-off with either throughput or actually turnaround, that's fine with me. Okay, so here it's going to be kind of like, we're not going to try necessarily to minimize the response time. Okay, but try to give it in average. We want a certain good response time. So now that we have this kind of criteria, let's look at the scheduling algorithms. And I'm going to start with easy ones. And we're going to start with first the family of non-preemptive one. And the other one is preemptive. What's the difference? Well, when you have a worker, once the worker starts working on the task, it doesn't stop until it's finished. That's going to be non-preemptive. Okay, it keeps working on this task until it's done. And then we're going to see the one that is preemptive, which is the worker might actually switch between tasks. Okay. So one, of course, is going to be good for batch systems. The other one's better for interactive systems. It doesn't mean it's exclusive. Actually, my computer, and probably yours, actually, what it does, it's a mix of both. Okay, you will see that at the end. So let's start at the first very naive scheduling algorithm. And this one is actually one that you know very well because it's first come, first serve. Okay, so like office hours, for example. Okay, so there's a queue, you go in the queue and then you wait your turn. Okay, when it's your turn, we consider that, we are running the task and we're going to keep running. I'm going to keep doing office hours with you until I'm done. Okay, so I'm not going to ask somebody else to come into the room and so on. Okay, so it's when they arrive. So let's look at it. Let's take a very simple example. We have first, a first task here, a program that takes 24 seconds. And then we have another one that will take only 3 seconds. And then the third one that will take only 3 seconds. Okay, meaning if I execute all of them in order, it's going to take me 30 seconds. What's my throughput? Well, my throughput here per second, it's going to be, I've completed three tasks in 30 seconds. So it's going to be 0.1 job per second. Okay, so that's my throughput. The idea here is like we're going to compare that with others, right? But, but what's my turnaround? My turnaround, remember, it's going to be the difference between the finish and the start. How long it takes to basically complete the task. Well, here it's simple, right? Because we never kind of stop. So here it's going to be the time it takes. So here it's going to be 24. Here it's going to be did I get? Yeah, okay. No, maybe I got mixed up here, but it's the same in the end. Here, the turnaround, it's correct. Sorry, it's correct. The turnaround here, so the first one is going to take 24 seconds. The third one is going to take 27 seconds to finish. And the third one is going to take 30 seconds to finish. Okay, so here, all of that divided by 3. In average, it takes 27 seconds to finish. Okay, my program. What's the wait time? So the wait time is like now, when exactly does it start? Okay, so here, the first one, 0. The second one is start after 24 seconds. And the third one after 27 seconds. So here, divided by 3, we wait on average 17 seconds. Okay, so if this was true for my entire system, it means like, when I start an app, I need to wait in average 17 seconds to start. Okay, it's going to make in average 27 to finish. Okay, so what's that? Well, what's the problem? And you know what's the problem, right? It's basically called the convoy effect. When you have people in front of you at the queue, well, if one of them takes a lot of time, well, you're stuck behind them. Okay, so all the process wait long for one big process to release the CPU. Okay, so if there is a lot of people in front of you, you're gonna starve. You're never gonna get the CPU. Okay, I mean never. Eventually you will get it, but it might take a long time. And actually, if one of them is an infinite loop, well, you will not get it actually. So let's look at another one. The other one is called shortest job first. And let's see how it compares. What's the idea here? We are going to reorder the process. Okay? Meaning, first I'm going to execute the smallest one. So in that case, here, I'm going to start with P2 and P3. They are both like 3 seconds. And then I'm going to do the big one after. So let's see, what's the difference? The throughput is actually the same, 0.1. So here, no, I'm not going to achieve more after a certain unit of time. The turnaround here, the turnaround, it's going to be different now. So for the first one, we wait 30 seconds. This one, it was only 3 seconds, and this one, it was 6 seconds to complete. Here now, the turnaround is 13 seconds. So now it means that in average, a process is going to be executed after 13 seconds. What's my wait time? Here, big difference. My wait time here, it's going to be 0 for the first one, 3 seconds for the second one, 6 seconds for the third one. Here, my average wait time is 3 seconds. Okay, every program here has started within 3 seconds. Okay, has started in average after 3 seconds. So you see here the wait time is huge compared to the first come first serve, right? And turnaround is actually also better, right? So this is a bit like me going in the hole saying, okay, let me know about your question. I'm going to try to evaluate. I'm going to try to do the thing, the fastest one first, okay? Because here I'm going to have the impression that I'm processing a lot of them, okay? What's the problem with that? We need to know, the process time in advance. Is that always feasible? Well, no. Okay, when you have a program, sometimes you don't know how long it's going to take to actually terminate. So here, this is actually kind of, for some cases you can do that, but for computers and process and so on, that's not going to work. Okay. So let's look at. We're going to try to optimize a little bit, and now we're going to look at the preemptive kind of algorithm. Okay, so I'm going to pause a little bit just to see if we have questions. Yeah, T-start is when it enters the queue. Yeah, good question, Kenny. That's exactly the problem. It's like we don't know how long they're going to take. That's exactly the problem here. Well, so to answer the question here, so I think P1 takes 24 seconds, P2 takes 3, and P3 takes 6. Well, no, because when you start them, you don't know whether they're executed or not. So this one is really going to take 30 seconds to execute, right? So here we assume that, again, this is kind of batch, meaning we have all this process. They all start at 0, and they're all ready to be executed. Okay, so that's the idea. Even here, the first come first serve, assuming that everybody comes kind of at the same time, and they form a queue. Okay, so let's try to improve that. So I'm going to look at the one. So my idea was not too bad actually. So I'm going to choose the small one first. Only the problem is I cannot evaluate the time it takes. So how about that? So here, yes, now I'm going to take into account when they arrive. Okay, so here, for example, you can have process 1 arrives at time 0, process 2 at time 2, process 3 at time 4, and process 5 after 5 seconds. Process 4 after 5 seconds, sorry. And then the burst time, meaning how long it takes actually to be executed, 7 seconds for this one, 4 for this one, 1 for this one, 4 for this one. So what's the idea with this shortest remaining time first? Okay, so when the new process arrives, okay, of course you're going to start executing. But then if you receive a process that takes shorter, that looks kind of smaller, well, you're going to execute it. So here, for example, I'm going to start executing P1. And actually here, it doesn't matter if you know how long, you're going to start executing it. Okay. And then you're going to execute P2, okay, until you finish. And then you're going to start with P3. Okay. You're going to execute P3 for a little bit. And then now you're going to go back to P2. Okay, because you were not finished with P2, right? And now you actually P4 come into the picture. Actually, it comes here. Okay, so now you execute P4, and then after that you finish executing P1. Okay, so if you do that, you can do the calculation. It's good because you optimize the waiting time. Okay, so here, as you can see, you're going to execute quite. These processes are going to start very, very quickly, right? So P1, for example, starts right away. P2 starts right away. P3 starts right away as well, right? So you optimize the waiting time here. P4 doesn't start right away, but I could have actually make it started right away. Yeah, I could have done that. I need to review this. But the problem with that is, it can lead actually to starvation. Okay, why? Because if programs keep arriving, okay, if you're a big process, well, they will kind of take a lot of CPU time. So this actually can lead to starvation. Okay, so we have a problem here. So another idea is round robin. And here, this is going to look like actually what I started to talk about when I started to talk about process. So here, what's the idea? We're going to have the time chunk into slices. We're going to call this slice quantum, and every time we're going to preempt the job just for the time of this quantum, and then once it's done, we're going to move to the next one. Okay, and we're going to move to the next one in the queue. So here, for example, I'm going to start P1, P2, P3. And again, P1, P2, P1. Okay? Actually here, again, I need to look at my numbers because if P3 arrive after 4, it doesn't work. Okay, it doesn't work. I'm going to correct that. But here, you understand the idea, right? So we have all the process and so on. We're going to try to give fair amount of time. And that's the kind of thing I was describing. This is actually good because you have fair allocation of the CPU. Okay? But the prime, and also it has very low waiting time. Okay, as soon as the process starts, it's not going to take a lot of time before it gets actually some kind of a CPU. So it's very good for interactivity. Problem here, if I were to be picky, every process has the same kind of fair access to the CPU. Is that good? Well, no, because on the system you want to be a little bit more. You want to give priority to programs. Here's an example. On my computer right now, I have two things going on. I'm streaming my video and I'm doing a backup. Which one should have highest priority? The backup, it doesn't matter when it gets completed. I don't care. Okay, so this one can have a slow priority. It doesn't mean I want to stop it. No, I just want to have a low priority, meaning it's going to get some processor time, but not all the time. But most of the processor time, I want to give a higher priority to my streaming, for example. Okay, so if I do that, well, I need to come with priorities. Okay, just quickly, I'm going to talk about this time quantum here. How do you choose how long a process is going to run for? Well, you have to take into account the context switching here. How long does your context switching takes? If at some point, the quantum of time is as long as the context switching, it's not going to be very efficient. Okay, so the quantum should be larger than the context switch. Okay, the context switch should be kind of insignificant. And the majority of the burst should be less than the quantum, of course, right? So you look at the programs, how long they take to execute. If you have the entire program fitting in one quantum of time, that's not a good kind of use neither, right? So the typical value in OS is between 1 and 100 milliseconds. depending if you want to have real time or not, right? But it's usually around those lines. So again, so why having priority? I told you, right? Because sometimes you have batch jobs, like stuff that you do on the backgrounds and so on, stuff that you can do sequentially, basically, or interactive jobs that require some CPU times. So how would you do that? Well, here's an approach. You can have multi-level SKU scheduling. The idea is the following. You're going to associate a priority with each process. Okay, so for example, you can say, I have process with high priority, process with medium priority, and low priority. Okay, imagine I have 3 levels here. I'm going to execute the one that have highest priority. Okay, so here, for example, I'm going to execute either P1, P3, or P6. Which one I'm going to execute? Well, within that queue, what I'm going to do is round robin. Meaning, they have the same priority, so they should be all executed kind of as soon as possible. I'm going to execute them into a round robin fashion. Okay, but only when this is empty, I'm going to move to my medium priority here. Okay, and same thing, when I don't have anything else here, I'm going to move to the low priority. Of course, this is good because I have my highest priority being, giving more CPU time than the lowest one, right? But you see the problem here. There are 2 problems. First, starvation. Okay, of course, if you keep having, high priority or even medium priority programs coming up, you will never execute those ones. Never. Okay, so that's a big problem. And the other one is, how do you decide on a priority? Okay, you might actually have that in your OS, saying, this program has priority high, this program has medium, this program has priority low. But otherwise, beyond that, how would you do it? You have a new program. How do you know which priority it has? Okay. For example, you would like to say a video game should have higher priority because it has to be kind of responsive more than just, Excel that is just going to wait for me to click stuff, right? So you see here, but there are 2 programs. How do you make a difference between those 2, right? The OS doesn't know beforehand. So there are some solutions. One is actually to prevent starvation. The idea is the following. You can increase the priority of a program with time. Okay, so at first maybe you start with like low priority, and if you see that a program doesn't have enough CPU, you raise the priority. Okay, why not? Or decrease actually. Same thing. If you see that the program has a lot of priority, I got a lot of computing, you kind of decrease the priority to give other kind of a chance, right? Why not? That's an idea, right? Or what you can do is the following. You can observe the process, okay? For example, it's a process that you have already seen. So you see what the process is going to do. You see whether it's going to be intensive. You see how long it's going to take, and so on and so forth, okay? Or you can look at, even if it's a new program, you can look at the I/O. Why? Because if the program is doing a lot of I/O, it means it doesn't have a high priority. Okay, it doesn't need to have a lot of CPUs. So maybe we can lower the priority. If it's calculation, because it's, for example, video games and it's doing a lot of graphics rendering and so on, well, maybe the priority should be higher. Okay, so we can have actually a smart scaling algorithm, if you want, that based on this observation is going to move stuff between queues. Okay, and that's actually what multi-level feedback queue scheduling is doing. Let me tell you, this is actually what's running in your machine, whether it's Windows or Linux. It has some difference, okay, but the general aspects are here in this slide. So here the idea is the following. This scheduling process is going to change the priority of the programs based on a set of rules, okay? And the 5 base rules are as follows. Of course, we're going to keep the same one as before, meaning if one process has a higher priority than the other one, it should run, okay? If 2 processes have the same priority, okay, we do round robin fashion, okay? So that doesn't change. But then we do these kind of things. When the job enters into the system, we place it in high priority, okay? Whatever the job. Why do we do that? Because we want to actually maximize response time, okay? We want this job to start, and we want to actually start measuring what's going on, Okay, so at first, it comes, we don't know anything about this program, we put it in high priority and we look at what's going on, we give it a bit of processor time. Once the job is kind of used up its time allotted, okay, so after some time, now we might decide to actually reduce the priority. Okay, so that's going to depend on the IOs, it's going to depend about a bunch of stuff. Okay, and we're going to start to kind of move it down to stuff. So that's why I was saying, my backups thing, my backup is going to do a lot of IO on the disk and so on. Okay, well, it can move down in terms of priority, right? But there's some kind of a safeguard here to avoid starvation. If at some point the scheduler realizes that there is a job with low priority that doesn't get enough CPU time, okay, or not at all actually after a while, you can decide actually to move it to the top priority again, right? So there's going to be some kind of a timer that says, okay, if after some time you didn't get any CPU, okay, I'm going to put you back in the top priority, and now we start again, right? It can start to go down again. So you see here, it's a very dynamic system. Okay, it's quite simple actually, but it turns out that this is the best way to actually schedule process. And guess what? The person who actually came up with this algorithm won the Turing Award for that. And that was invented actually in the 70s. Okay, so it's quite old. And that's this kind of algorithm that we have in our OS. And guess what? That's what you're going to have to implement for project one. Okay, where you're going to actually implement the context switching and so on, and the scheduler for the process. Okay, so that's coming next. Again, this is just one slide. If you need to know more about that, there is always the readings. The reading contains more maybe details and so on, but you will also practice it, so that's going to help you understanding this thing. So what's coming next in the course? Here, as you can see, we are using process. And process, they have their own files, their own variables, and so on. They have a PCB, and we manage those processes. Switching context between process can be very expensive. Okay, so because every time we have to save the registers, we have to switch stuff around, and so on and so forth. Also, communicating between processes is expensive, right? They don't share values. Okay, again, when you create a child thread, it's a copy. But after that, if you modify the values, the parent process will not know. How do you kind of synchronize? How do you exchange values? Well, you have to do some inter-process communications, and you have done it actually in BO9. It's signals, it's signals mainly, right? But pipes as well, and so on. Doing that is actually expensive. What if a program needs multiple processing, but kind of in a nutshell? Okay, so for example, Firefox, for example, is gonna have all my tabs inside separate threads. Okay, because they are going to manage their own input/output there and so on. Okay, so here actually this exists in Unix system. It's called threads, and I don't know if you have seen that in BO9. Let me know if you haven't seen it. There is a difference between threads and process. Okay, and that's quite important. So next time we're going to see threads. Let me know if you have not seen that in BO9, because maybe I need to spend more time introducing threads. But if you have seen them, maybe I'm going to go a little bit faster. Okay? So that's coming next week. Again, so that's some acknowledgements. So just to go back, and maybe I'm going to switch back to the camera. So again, here what we have done is just managing all these processes and scheduling them. Okay, I haven't talked about memory. I saw some questions on the chat about the memory aspect. That's gonna come next, right? But that's also something that we're gonna take care. But just in terms of process management, it's something that you're gonna practice into project one. Okay. So let me answer questions. We don't care about IRQ priorities anymore. Oh, we do care. we do care about hierarchy priorities. But again, this is something completely orthogonal, right? So I told you the interrupt whatsoever, it's going to be executed. I mean, the scheduler is not even involved, right? The scheduler, that's something part of the OS. When you have an interrupt, for sure, the CPU is going to stop and then execute that. There is no scheduler there, okay? So don't confuse the two. We have not seen threads. Okay, well, we are going to look into it. So why not use it to set priorities? That's Jackson. Oh, that was about the RQs. Well, it's two different things, okay? Actually, one process can use multiple inputs, and so it's gonna, by default, they will be like multiple interrupt used, right? So it's completely orthogonal. It's two different systems. So don't confuse the interrupts with the actually process scheduling, right? It is really not the same thing. Hopefully, if you are a bit confused, that's okay. Hopefully, after the project, it's going to be more clear. Okay? All right. So I'm going to stop here. Again, I will have office hours tomorrow for any kind of questions. The office hours are going to be on Blackboard. The TAs have office hours, the TAs have tutors. Please use them, participate, and so on. Okay? Thank you very much, and have a good day, and see you next week. Bye.